Sorting. Sorting is hard. So far we've looked at bubble sort and insertion sort. These algorithms are fairly simple to program, but now we're going to get more serious and look at some faster sorting algorithms. Today we're going to look at Quicksort. Quicksort is what's known as a divide and conquer algorithm. The most important part of Quicksort is choosing a value called the pivot around which to partition your list. In other words, to split the list into sublists. This particular algorithm just uses the last value in the list as its pivot around which to partition the elements of the list. At the very top, the first time the list was split, 70 was chosen as the pivot, and then all the values less than 70 were put on the left, 10, 30, 40, and 50, and all the values greater than 70 were put on the right, 80 and 90. And then we just repeat this process on both of the splits. On the left, we choose a new pivot of 50. Now it turns out that all the values are less than 50, so 10, 30, and 40 go on the left, and nothing goes on the right. That's not ideal. We would prefer to split up our list so that there are some values less than the pivot and some values greater than the pivot. We'll get into different ways of choosing the pivot in a moment, but for now, just notice that the algorithm repeats itself on each smaller list, and then we compile all the lists back together into one final sorted list. In this visualization of Quicksort, one item is chosen as the pivot in red, and then that blue line shows sort of the division between the values that are less than the pivot and the values that are above, and we divide the list into halves. And then we divide the halves into halves based on are they above or below the new pivot. Lastly, the pivot is placed in between all the values that are less than the pivot and all the values that are greater. Quicksort runs most efficiently when about 50% of the values are less than the pivot and 50% are above the pivot. So in this example, on the second round of partitioning, when we choose 50 as the pivot, that's not a very good choice. It would be better if we chose something like 30 or 40, where at least some of the values would be below and some would be above. There's no single best way to choose a pivot. The first two ways are very simple. We either choose the first element or the last element as the pivot. Randomly choosing the pivot can be a way to protect our code or our application from someone who might choose to submit a list that is particularly hard to sort in order to slow down our algorithm or our application intentionally. A lot of computer science actually worries about this sort of thing, where we're looking at what is the worst case and what might an adversary do if they were trying to, for example, perform a denial of service attack on our application. Choosing the median as the pivot is actually ideal, but there's the extra cost of having to calculate what the median actually is. What's important to remember about the pivot is that you're trying to use it to create two lists that are
perfectly balanced, as all things should be.
There's a variety of different ways to write code that all do quicksort, but have a few different features. For example, when we looked at the previous two sorter algorithms, one of the things that we were curious about was, is the algorithm in place? In other words, can it sort the list that it's given, or does it need to copy all those values to a new list? The algorithm that I'm showing you currently for Quicksort copies all the sub-values to separate lists. So I started off using 5 as my pivot, and I copied all the values that were less than 5 to a whole different list, similarly with all the values that were greater than 5. And then I picked my list on the left, and I used 4 as my pivot, just randomly picked it out of there. And then I sorted all the values that were less than or greater than 4. Now, it turned out that all the values were less than 4. Now I'm doing the same thing with 6. Now, of course, we know that 6 is right next to 5 and there's no duplicates, so all those values are going to be greater than 6. Those aren't great pivot values, unfortunately. So sometimes we get unlucky and the pivot turns out poorly, but sometimes it works out pretty well. This is the simplest way to do Quicksort. The next two ways that I'm going to show you are a little bit more complicated to write the code for. Differences in Quicksort are all differences in how the partitioning is done. There's an outer level of Quicksort that is basically always the same, and it's a recursive function. Quicksort calls itself. Here is some pseudocode, and I'll dive into the details. So our Quicksort algorithm takes 3 arguments: an array, ARR, or list to be sorted, a low index of values to start with, and a high index of the values to start with. So we want to sort all the values between the index of low and the index of high. And we're only going to do this if low is less than high. So we partition the values, and we get the partition index. What that means is that after the partition function is called, we've got all the values that are less than the partition left of partition index, pi, and all the values that are greater than the partition are higher up in the list than the partition index. And we're only partitioning between the indices of low and high. And then we have the recursive calls to quicksort. We're going to quicksort all the values that are left of the partition index, and those are going to be the values between low and the partition index -1. And then we're separately going to sort all the values that are greater than the partition index, and those are going to be the values from the low value, the low index of partition index +1 to high. Getting back to the differences, we've already seen one partition algorithm that basically just throws all the values less than the pivot into one list and all the values greater than the pivot into another list. However, there are two more popular partition algorithms that are in place, don't require extra lists or extra memory. One was invented by Tony Hoare and the other was invented by Nico Lomuto. We're going to start with Lomuto's partition. Lomuto's partition uses the last value in the list at the high index as the pivot and then advances two values left to right through the list. The first value is I, and this is going to be basically the index that is immediately to the left of the values that we've checked that are lower than the pivot. The second value that increments through the list is j. It goes from low to high in this for loop. And this is where we're going to iterate over the list and check each of those values in turn and decide if we need to put them before this I index or if we can just leave them where they're at after it. There is a swap that occurs. This is a swap right here. So if we find that the value in the list at index j is less than or equal to the pivot, then we're going to increase the I variable and we're going to swap I and j in the list. And I'm going to show you what that looks like with a deck of cards in just a moment. At the very, very end, we need to put the pivot properly into its location in the list. So we do that with this swap right here. We swap high, which is itself the pivot, right? We defined it up here. And then we also swap I+1, which is the value right after the last lowest value, the last value that we found that was lower than the pivot. Finally, we return the index of the pivot itself, which is going to be I+1. Here's what Lomuto's partition looks like with these set of cards here. On the far right, I've got this origami ball, the yellow and blue ball there. That's my pivot. I'm using this red and gold battery as variable I, and the little hair tie here as index j. So I'm going to start off by comparing this 3 right here to the pivot, 6. It is less than the pivot, so I'm going to swap I and j right there. I'm going to move I forward 1, and j is just going to naturally increase forward because that's what the for loop's going to do. So now I'm going to compare 2 to 6. It needs to also swap. It's less than. Right, I, the battery right there, is always going to stay right ahead of the values that are less than the partition. 7 is not greater than 6, so I only move j forward. I only move the hair tie forward. Now I swap at the value I, which is 2 indices backwards, right? It's 2 places back. The I and j are no longer at the same place. 9 is not less than 6. 8's not less than 6, so j keeps moving forward. Now 4 is less than 6, so I swap it with the value at index I at the battery, move the battery forward, and now I'm done. I've reached the end of the list here. I still need to swap my pivot value 6 at the location I, and now all the values on the left are less than 6 and all the values on the right are greater. Before we look at the code for Tony Hoare's partition, let's check it out as a dance. This time we're using as the pivot the lowest index value in the list, number 3. So the hat on the far left. We just compared with number 6 on the far right. There's going to be an index that's moving down through the list. Compared with 6, compared with 9, those are both greater than 3, so no changes yet. 3 compares with 4, and there's no change there either. So this index, the other hat, keeps getting passed right to left through the list. Number 3 is going to compare with 2. And these two are going to need to swap. And something really interesting happens right after they swap. Previously, we were counting down through the list. 9, then 8, then 7. We were looking at the later values. Now there's an index that's going to move up through the list. We compared with 2, the pivot compared with 2, then pivot compared with 0. Now the pivot's comparing with 1. We see that there's an index going upward through the list, shown by the passing of the hat from left to right. The pivot number 3 is going to compare with 8 here, and they're going to need to swap. And then what happens is that index changes direction. Instead of comparing upward through the list, now we need to move down. The only person we haven't compared with yet is number 7, which happens right there. At this point, the first pivot value, number 3, is in its final location. So he's going to turn his back to the audience there, and now there's going to be 2 lists, one that is less than 3 and one that is greater than. Now the list on the left can start sorting itself in the exact same fashion, and when they're finished, the list on the right is going to sort itself in the exact same fashion. And one thing that you might note about this is that if we have multiple processors on our computer, Quicksort is a great algorithm because of that divide and conquer feature, that we could ask different processors to sort the different lists. There's not going to be any interaction anymore between the lower list and the upper list. So now we're looking at Python code for Hoare's partition. Now I said that there was an index moving down through the list and an index that moved up through the list, and they're actually saving those as 2 different values, and that's important so we can switch back and forth and remember where we left off. The pivot is that lowest value in the list, just arbitrarily selected. There's an outer while loop that continues until the 2 pointers run into each other, at which point we can return j, which is going to be the index of the pivot. We've got a while loop right here. As long as the values at index I are less than the pivot, we're going to keep advancing I through the list. And then there's a while loop here. As long as the values at index j are greater than the pivot, we're going to keep decreasing j through the list. And now at this point, we know that the value at index I is actually greater than the pivot, or equal to it, and the value at index j is actually less than or equal to the pivot. And that's not what we want. So we're going to switch those 2 values, and then we're going to go back up to the top and start looping through again, checking to make sure that the values at index I and lower are less than the pivot, and that the values at index j and greater are greater than the pivot. Let's look at Quicksort's performance. In the worst case, Quicksort is just as bad as bubble sort or insertion sort. It's order n squared, and that occurs when we're choosing the wrong pivot each time, such that one of our lists is all but one value, and the other list is totally empty. So in other words, we choose a pivot that's either on the low end or the high end of all the values that we're trying to separate. But the best case performance and the average case performance is significantly better. It's n log n. That's n times the logarithm of n. And usually that logarithm is base 2 because we're dividing things in half. How much better is n log n compared to n squared? Well, here are the graphs in Desmos. So you'll notice that the n log n graph in blue grows much more slowly compared to the n squared graph, which is what we want because our x-axis here is basically how many numbers are in the list. And as there's more numbers to sort, we don't want our algorithm taking so much more time. The space complexity, or amount of memory, depends a little bit on the implementation. It could be order n, so linear, or it could be order log n. Now it's not shown here, but the algorithmic paradigm for Quicksort is divide and conquer. Also worth noting, a reminder, that Quicksort is a recursive algorithm. Quicksort can be performed in place, meaning we're not going to copy all the values to some other list. Quicksort is not stable. The most efficient versions of Quicksort, the ones that we've looked at, do not guarantee that 2 values that are equal may not be swapped. And this is because one of those 2 values might get chosen as the pivot. Quicksort is certainly the most complicated sorting algorithm that we've looked at so far, but I hope you'll agree that the benefits of a quick and efficient sort are worth it.